everyone. My name is Baganis. I'm a doctoral student of EMPA and DPFL at Switzerland, and the topic of my presentation is the fabrication of metal-metal composites using a hybrid fabrication process that includes both additive manufacturing and induction melting, with the emphasis given on the combination of stainless steel with copper. So at first, I'm going to spend a few minutes talking about, in general, the idea of metal-metal composites, and particularly about the fabrication process that we use for the fabrication of our samples step by step. While at the main part of the presentation, I will focus on some basic microstructural analysis, with the emphasis given on the interface between the copper and the steel part. And finally, I will show the first results from our neutron imaging and tomography measurements that we have conducted at Paul Scherrer Institute. So, to begin with, I think that in general, all of us are familiar with the idea of the metal matrix composites. We have a metallic matrix where we disperse a secondary phase, usually a ceramic material, in order to achieve a final structure with increased strength and hardness and maybe even wear resistance. So, what is the difference with these metal-metal composites? The idea here is to try to disperse as a secondary phase a pure metal or an alloy in order to achieve also an increased ductility of the final structure. To be honest, there is no specific definition, so we can easily say that the metal-metal composite is a special category of metal matrix composites, or even a special category of bimetal structures. But I think that this term is better in order to distinguish it based on some more characteristic geometries of bimetal structures that we may see at welding or additive manufacturing. So, until now, I have seen in the literature multiple different fabrication processes used for the production of these composites. In many of them, at least one processing step includes the use of powder metallurgy. So it is quite common to pre-mix the different powders and then result in the formation of structure with process like milling or hot processing, where based on the composition that we have, we know that there is an expectation for a specific volume fraction of the dispersion phase. There is also the ability to use conventional casting process, and maybe the older one that have been seen is the use of extensive plastic deformation techniques. So usually by rolling or with extrusion, someone can end up having some characteristic fiber-shaped reinforcing phases. Obviously, and as expected, additive manufacturing has gained interest during the last years for the production of these materials as well. The simplest case for someone is to use methods like laser powder bed fusion and having pre-mixed materials ended up in a specific fraction of the secondary phase as with milling or hot pressing. Or someone can go with direct metal deposition, use multiple powder feeders, and say that one feeder will be for the matrix material and the other one for the reinforcing phase. What we try to exploit using laser powder bed fusion is geometrical freedom, or freedom which gives us the opportunity to design complex structure with lower processing time and with only one processing step. So the idea here is to design structures which will play a dual role. The first role is to be the reinforcing phase of the composite material, and secondly, to play the role of mold, inside of which we will later on infiltrate the powder, and this powder will be melted using induction casting. So, at first, and we used the commercial software NetFab from Autodesk, and we designed two principal geometries. The upper one, this one, is a lattice with an overall height of 2 centimeters, which is split into two parts. The lower part has been incorporated with some struts or a grid structure where we plan to infiltrate the powder and create the composite material, and we have an upper part which is empty. The reason is that in general, at the beginning of the process, we want to have more powder because we expect a packing density of the powder around 50% of the bulk material. Second geometry is the cylinder. Although from this slide it is not obvious, the overall size of this cylinder is much bigger from these lattices. It's an overall height of 45 millimeters. And once again, we split this geometry into two. We have the upper cylinder with a diameter of 13 millimeter, which plays the role of powder holder, and the lower one with 15 millimeter, where we have designed these internal lattice of 316L. These parts are connected to one another with a hole that will lead the molted copper powder from the upper to the lower part. So, as a first step, we use laser powder bed fusion, and more specifically the SISMA machine. I think that if you have seen already one presentation from EMPA, you already know about this specific machine, and we use the same scanning strategy for both lattices and cylinders. We played with a laser power of 125 watts. We used a unidirectional scanning strategy with a rotation of 90 degrees between the successive layers. Then we use induction melting. We have a laboratory-based furnace at EMPA in Dubendorf. And what we do is that we put the sample inside a graphite mold, which is surrounded by the induction coil. So we play with the creation of alternating electrical and magnetic field within the sample, and we will end up heating the copper powder through the Joule effect. The heating cycle that we used for melting the copper powder starts with a heating rate between 2 to 5 Celsius per second. We keep the material above 102,000 Celsius for 5 minutes, and then we cool down with a cooling rate of around 5 Celsius per second. So we end up by fabricating some composite structures. One, we can see that we have the copper matrix, inside of which we have this internal lattice that we bring with laser powder bed fusion. Later on, we also machine the sample in order to get rid of this contour structure. So, the reason for playing with steel and copper, not only for this process, but in general with the multi-material approaches, is that from the one side we can have the high strength and the corrosion resistance of steels, in particular stainless steel, and on the other side we have the thermal and electrical conductivity of copper alloy. This is a combination that can have potential applications in the future. We know that 316L stainless steel is one of the most characteristic representative grades of austenitic stainless steel, with possible appearance of a small amount of ferrite based on the scanning strategy. And this copper chromium zirconium alloy has a low amount of chromium and zirconium, no more than 2% and we expect to have the copper matrix, and based on the scanning strategy, we may have a percentage of some copper zirconium precipitates or segregated chromium. So, from the analysis of the microstructure, we can see the copper matrix, inside of which we have these ellipsoids, which are part of the reinforcing structure of 316L stainless steel. And by having a look on the interface between the steel and the copper, we see this characteristic layer, the width of which is around 50 micrometers, with this island-shaped structure, which is a first sign of good metallurgy, the creation of an interdiffusion zone between the different alloys. What we saw from the steel part is that we do have the appearance of some small pores, but the porosity problem is more intense on the copper part. This is something that we're going to discuss more analytically later. Now, by having a look from the EBSD analysis, as we can see here, it is obvious the result of the scanning strategy that we have used for 316L stainless steel. So you can see this rectangular structure. We bring unidirectionally, and then we rotate by 90 degrees. So this is the reason for creating these patterns. Actually, the width of these patterns are equal to 100 micrometer, which is the hatch distance that we have used. And we can see the appearance of the 001 texture in the middle of the scanning tracks, and also we have the appearance of the 101 texture. We also see that this interdiffusion zone has been recrystallized, and as expected based on the casting conditions, the copper part has bigger grains and a more random texture. Now, speaking about the faces, what we observe is that in the interface between the copper and the steel part, we see the appearance of the BCC structure. Initially, by having a look on this BCC structure, three possible scenarios could explain its appearance. Theoretically, it could be ferrite from the printing of 316L structure. However, this scenario cannot be feasible because of the specific position of this BCC structure, and based from some XRD patterns that we saw that practically only austenitic phase appearing after the printing of steel. Second explanation could be segregation of chromium, but the most prominent one is that during the casting of copper, we have an indirect heating and cooling of steel, so we result in a phase transformation from austenite to ferrite. By having a look on the interface using ADX analysis, we see that this region, the region that we observe the DC phase, has a gradual depletion of nickel. The nominal composition of austenitic steel for nickel is 12%. At this interface, it's around 5%, and there is an increase of the presence of chromium. So from the nominal composition of 18%, we ended up having a composition of 35% chromium. And we also see that there is a gradual composition transition between the steel and the copper. Finally, in order to have a look on the crack and the porosity formation, we conducted some neutron blood edge imaging and tomography measurements at Paul Scherrer Institute. For both of the measurements, we used the cold neutron-based beam lines, BOA and ICON, and we had the option to went either from neutron radiography, neutron imaging, or neutron tomography. The latter, which is the one that we paid attention more, we can reconstruct the sample by focusing on distinguishing the steel and the copper. And from the first analysis, we can see the appearance of porosity at the lower interface between steel and copper. The second measurements have been done once again using the ICON beam line. Just give me a second. So here we examined the cylindrical structure. Actually, we examined the lower part of the cylindrical structures where we had printed the internal lattices. Due to geometrical restrictions, we cut the sample into two. So at each time, we examined a sample having a height of 12 millimeter and a diameter of 15 millimeter. We start by having as a reference the as printed structure, and then we move on with the cast structures, having 625 projections, for example, and an exposure time of 150 seconds. So the aim here is to have a 3D reconstruction of the sample, emphasizing on the formation of porosity and cracking. For the as-printed structure, we notice that in general we don't have intense presence of porosity, especially at the contour part, but we do have some smaller pores around 0.20 millimeters appearing at the edges of the internal structure. For the as-cast structures, we see the appearance of porosity at the interface between the contour and the casted part. Actually, this porosity is like a plane, so we can talk about a detachment between the copper part and the steel part, and we can attribute this one, for example, to shrinkage of material during to its solidification. Secondly, we can see also the appearance of cracking at the central part of the sample. Some problems are also detected when having a look at the upper part of the sample. So this one was the lower part, and this is the upper part of the sample. And again, the appearance of this porosity can be attributed to some geometrical configurations, as this is exactly the part that connects the hollow part of the cylinder with the lower part where we have the internal lattice. But in general, we can say that the interface between the steel and the copper are free of cracks, at least at the left and the right part. So the majority of the problems are focused on the central part of the structure. So, to end up to conclusions, until now, what we have done is to use laser powder bed fusion with induction melting for the fabrication of composite materials. We believe that in general, the process can have application to different combinations of alloys. So, in principle, what we need is to have some samples, some alloys with good printability, like steel or titanium or nickel-based superalloys. And on the other side, we need we need powders that can be casted with induction melting. Copper is a good example. We have also tried it with aluminium, but in that case, the spheroidization of the powder due to the alumina layer results in intense presence of not filled lattices, so we have intense presence of porosity in between the steel and the copper part. We also see the appearance of this ferritic layer with a width of 50 micrometers. This is something that we should pay attention on how to thermodynamically analyze the appearance of this ferritic layer. We have the appearance of porosity in cracks, and this is the reason that we will develop more complicated heating cycles, maybe introducing a first heating step of sintering in order to get rid of this porosity, because this is the critical step that should be overpassed in order later on to assess the mechanical performance of the structures. Thank you very much for your attention.
Thank you.